Hello, everybody. Welcome to our 11:30 and final press conference of this meeting. Titan, as you've never seen it before, new results from the Cassini mission to Saturn. We have 5 speakers, and they'll be speaking in this order. Steve Wall, Cassini Acting Radar Team Lead from NASA's Jet Propulsion Laboratory in Pasadena. Randolph Kirk, Cassini Radar Team member with the U.S. Geological Survey Astrogeology Science Center in Flagstaff, Arizona. Marco Mastro Giuseppe, he's with the Cassini Radar Team Associate from Sapienza University of Rome in Rome, Italy. Jeff Cargill, who's Senior Associate Research Scientist at the University of Arizona in Tucson. And Linda Spilker, Cassini Project Scientist. She's also with NASA's Jet Propulsion Laboratory in Pasadena, California.
Okay, thank you. First slide in my presentation is basically a big orange ball, and a big orange ball is what you'd see if you looked at Titan with your eyes close up. In 1980, when we saw that, we knew that that meant methane in the atmosphere, and that means liquids on the surface. But when Cassini arrived in 2004, it had a radar mapper that releases bursts of microwaves that go through the haze, and the echoes of those off of the surface allow us to look at pictures. So with radar eyes, you see not only liquids, you see seas, and you see rivers flowing into the seas, and you see drainage networks making up those rivers. You also see mountains and mountain ranges, and you see sand dunes. In short, we see a very Earth-like world from a place that's 200 degrees below 0 centigrade, or almost 300 degrees below 0 Fahrenheit. So this is a very alien place that looks amazingly Earth-like. With radar eyes, we collect one strip, like you see on this slide, every time the radar operates as we go past Titan. But I think you'll see that as you collect enough strips, it begins to turn into a map. And with a map, you can see the relationship of one feature to another. And that's important, as we'll see. So what we're going to do today is we're going to hear from 3 speakers who are going to tell us 3 different pieces of this puzzle that is Titan. So the next slide is titled What You'll Hear Today. We'll hear a talk about how the arrangement of these lakes and seas on Titan tells us something about what's under the surface and might tell us something about how these seas were formed. We'll show that the echoes that this radar puts out sometimes not only bounce off of the surface, but they also bounce off of the bottom of these seas, which allows us to tell how deep they are. Once we know how deep they are, we can tell the volume of the hydrocarbons, and we can say something about what kind of hydrocarbons might and might not be there. Finally, we have an outside expert on Titan who is not part of the Cassini science team, but will show us some perspective about how what we've said relates to the north part of Titan in general, both liquids and solids. Just a few comments on the overall view here. If you're going to understand planets, you need to look at more than one of them. Just like if you're going to understand a car, you need to look at more than just a Cadillac or a Model T Ford. And so what we're trying to do here is to relate things that we recognize to places that we don't recognize. And that's important for many reasons if you're going to look at other planets, not only in our solar system, but in other solar systems. In particular, the hydrologic system on Earth, where it rains, rain collects in seas and then evaporates and rains again, is very similar to a cycle on Titan, which we could call the methanological cycle if we want. It rains, the methane collection in the seas, and that evaporates into the atmosphere again. So with that, I'll turn it over to Randy Kirk, who will talk about the relationship and our new mosaic.
Okay, thank you, Steve. As Steve just said, the idea that there might be bodies of liquid on Titan, liquid hydrocarbon, goes back all the way to the 1980s and came up basically for chemical reasons, that there might be a reservoir of liquid methane on the surface supplying the atmosphere. So when we got to Titan with Cassini in 2004, we were very eager to see this, and the first few images we got showed no such thing. They showed dry land areas. Next slide, please. But as of about 2006, we had our first flyby over the North Pole of Titan. Next. And that resulted in a paper that actually took the cover of Nature the next year in 2007, This is the image strip. It's sort of foreshortened to look like a perspective view looking across the north part of Titan, and those dark areas are bodies of liquid hydrocarbon. I should hasten to point out that this image and the ones you're going to see throughout the talk are artificially colored just to emphasize the liquid bodies. They are, the radar does not see colors the way the human eye does. It gives us black and white images, but we've tinted the lakes bluish just to emphasize where they are. And they're radar dark basically because they're smooth and don't give a return of signal. The first author on this paper, next, was Dr. Ellen Stofan, who's a member of the radar team, and she is now the NASA chief scientist. So fortunately, she has a good sense of humor and did not respond too badly when we put her on the cover of a package of butter for discovering the land of lakes. Well, about the time this paper was coming out, Titan was continuing to image the North Pole of Titan. Cassini was, and we discovered much larger bodies of liquid. And we now had multiple images crisscrossing the North Pole, and we put together a map. Next slide. This was press released in 2007, and we were immensely proud of the coverage we had then, showing the area around the North Pole down to about 60 degrees north. And there are 6-7 high-resolution image strips in here and some lower-resolution coverage. And we saw what appeared to be kind of a split personality to Titan's north, where on the left side of the map you see mainly small lakes, 50 kilometers and smaller, so 30 miles and less across. And on the right-hand side, some very large bodies of liquid. The one at the top that's sort of heart-shaped is called Ligeia Mare. There's a suggestion that several of the other pieces that we happened to go across with our image strips were connected in a bigger body. In any case, that was given the name Kraken Mare. And unfortunately, this was all we saw for several more years. We got an additional image, but it covered the same area and let us look for changes. But Cassini was busy in the next few years imaging the south pole of Titan, where it found only a few very small lakes, and the equatorial regions, where there were plenty of interesting features but no evidence of liquid hydrocarbons. So it was about a year ago that the nature of the mission brought the spacecraft back to the North Polar area, and we started building up new image coverage. And the next slide shows the mosaic that we've made from this coverage. We've gotten quite a few more high-resolution image strips. There's some medium-resolution imagery covering the area at lower right, which contains Kraken Mare. And I've actually filled in some of the holes with very low resolution coverage that doesn't show a whole lot of geology, but is good enough that if there were any major seas in there, we would certainly notice them. So this is the map, and you will notice that it is not so much a split personality between left and right with lakes on one side and seas on the other. Instead, all of the major seas are in an area that is actually almost rectangular. Next click, please. I've outlined it there with a box. And the remainder of the area around the pole, all the way from 6 o'clock clear around almost to 3 o'clock, is filled with these small lakes. And we have a few gaps where we haven't seen, and the other instruments on Cassini show that they have small lakes in them too. So there seems to be a pattern of just a polar region of small lakes, and then something interesting and different happening in this rectangular box. What could that be? When geologists see straight lines, they immediately jump to the idea of what's called tectonics, which basically means faulting. Fracturing of the crustal materials is a great way to make straight features on the Earth and on many other planets. And so a possible analog for this rectangular area of kind of elongated seas with coastlines that you might notice kind of parallel the edges of the box is in the next slide. This is the western U.S., the state of Nevada, and there's a topographic map on the left. And you notice all the parallel mountain chains. This is called the Basin and Range Province. And there are straight-sided mountain ranges and alternating with valleys as a result of the area being pulled apart by the forces of plate tectonics and breaking up into these separate ridges. And the illustration on the right shows what it would look like to fill in the low areas with liquid. which is not just hypothetical. Actually, about 12,000 years ago, during the Ice Age, when the evaporation was less here, the area actually did flood, and geologists have found shoreline traces outlining the area shown, which I argue is pretty reminiscent of what we're seeing in that box of seas on Titan. Elongated bodies of liquid, narrow straits connecting them, long skinny peninsulas, a kind of fabric of things that are more or less parallel and connecting at right angles, and even, next, the outline of the whole flooded area fitting into a fairly rectangular box. So something is going on, we think, causing tectonic activity in this one part of Titan's northern hemisphere, creating low areas, large low areas that fill naturally with liquid and create the major seas. Why that's happening there, we really don't know yet. The rest of the polar terrain is, as we said, covered with small lakes. And next slide, please. We think there might be terrestrial analogs for these as well. What creates little roundish blob-shaped depressions that can fill with liquid? Well, one possibility we've discussed in the team is volcanic activity. Next, Steve. This is, of course, the most famous example. There are many volcanic calderas and craters on Earth that have lakes in them. One of the problems with explaining all these little lakes on Titan this way is that although we see some evidence for what we think is volcanism elsewhere on Titan, there's not a lot of volcanic features, and to suddenly have one area around the pole where there's hundreds and hundreds of volcanoes hosting lakes would be a little unusual, perhaps a little unlikely. The other thing that we've talked about primarily within the team, next, is processes of dissolution, where the groundwater on Earth can dissolve materials like limestone and create sinkholes that then fill with liquid and form lakes. And the comparison there is between the bottomless lakes in New Mexico, where a bunch of us from the radar team actually visited a few weeks ago to look at these features, and a much larger but very similar appearing pair chosen out of the many lakes on Titan. So on Earth, it's soluble rock dissolving in groundwater. Obviously on Titan, at hundreds of degrees lower temperature, H2O is a solid material. The liquid is hydrocarbon, methane, and ethane, as we've heard, and whatever it's dissolving must be something rather different too, not limestone, not ice, but probably solid organic materials. Now, the other thing that happens when you have a crust of soluble materials on Earth and groundwater is under the surface you tend to get caves, and so it's kind of an exciting hypothetical prospect that the underneath the North Pole of Titan there's a network of caves. I can't tell you if that's true, but next slide, I can tell you definitively that if you go in caves on Earth, you'll find a lot of Titan scientists in them nowadays. This is from the same trip that we went to New Mexico recently. Okay, the other thing that all of this new coverage of the North Pole has brought us is, in addition to completing the map, the images tend to overlap each other. And where that happens, they actually function as stereo pairs. And so my group, next please, in Flagstaff has developed the tools to take those stereo radar images and produce topographic models. And I'm going to show in a moment a short flyover movie of the seas and lakes showing you the different character of them. I should say at the outset that this is vertically exaggerated by tenfold and of course false colored as well. And you'll notice that there are lumpy areas and smooth areas even within this still that we're starting out with. That's because we don't have stereo coverage over the whole North Pole. We wish we did. It's less than half. And so we have topographic data for parts of the flyover, and other areas we just are using a smooth surface. So Steve, if you'd start the movie. We're going to start at the southern end. There's the North Pole. And we're zooming into the southern end of Kraken Mare. There's some stuff that looks like little islands in there. That's just noisy radar data sort of alternating with better quality No topo data there. As we fly up now, we see the island Maida Insula and some highlands, and we're flying over the second largest sea, Ligeia, where you see archipelagos of islands and very rugged coastline. It's an area that looks like it's been eroded, and then the liquid level has raised up into the river valleys. Now, this area is not as smooth as it looks. We're just off the topographic map and turning around through the area of these small lakes, again, about 50 kilometers across, and now we have some more topographic data here, and you see the lakes nestle into the little valleys in between mountain ranges and a lot of very rugged terrain. And the data in the movie end at about the same latitude where the land of lakes stops, and we're back to sort of normal equatorial Titan. So that's my part of the presentation, and I'll turn it over to Marco now to talk about actual measurements of the depth of one of Titan's seas.
Thank you very much, Randy. I'm going to talk about the recent results we found with Cassini radar. These results answer to the question, what is the depth and composition of the second largest sea of Titan? Next slide, please. So my presentation will focus on this main point, which is why we want to know the depth of the sea, why right now, how we did it, what we found, and what are the implications. Next. So about 7 years ago, Cassini radar has shown for the first time the presence of liquid body on Titan. The first natural question was, what is the depth of this liquid body? In this very beautiful mosaic image generated by Randy, we can see all the northern hemisphere of the moon and all the lakes and seas that has been already mapped by the radar. Cassini scientists have been also calculating the area of these lakes and sea, but we want to know more. We want to know also the volume and the composition of the liquid. Next. So we are able to answer at this question right now thanks to the results obtained from a spatial observation of Cassini. The radar is able to work in different modes such as imaging or altimeter mode. In altimeter mode, the radar points its antenna to the nadir direction and is able to obtain topographic information of the moon. And during the T91 Cassini flyby, the radar is pointing the antenna to the second largest sea of Titan, Ligeia Mare. So, next slide, please. By processing the data using techniques that we usually apply for radar sounders on Mars, we were able to extract information from the surface and from the sea floor. In this graph, we can see the first strong peak reflection from the surface, followed by weaker reflection from the sea bottom. Then by converting the time between the peaks, we were able to obtain the depth of the sea. Next slide, please. On this image, we can see all the data, the processing of all the data over the lake. We can see the thick red line, which is the reflection from the surface, followed by a fainter curved line underneath, which is the reflection from the bottom. So for the first time, we were able to get the topography of the subsurface of an extraterrestrial sea. Next slide, please. So what we found is that the maximum depth of the sea of Ligeia is about 160, 170 meters. From the surface area, we were also able to calculate the average depth of Ligeia, which is about 70 meters. In some way, this number can be compared to Lake Michigan in US, where the maximum and average depth are similar to Ligeia. Next slide, please. So we found that because the radar was able to plumb the bottom up to 170 meters, the liquid must be very, very clear to the radar eyes. Also from topography of subsurface, we found that the northern part of Ligeia is shallower with respect to the south part. So who knows, maybe if some one of you want to snorkel on Ligeia Sea, maybe it's possible even to see the bottom at the north part. So next slide, please. Another important results that we found, we were able to extrapolate the total liquid volume of Ligeia, which is about 9,000 cubic kilometers, or the corresponding 5,000 gigatons of hydrocarbons. This is about 40 times the proven oil reserves on Earth. This work was led by Alexander Hayes, the guy there, and that is collaborating with us, and he is co-author now of a work which is being to be published very soon. Next slide. From radar measurements and from recent laboratory results obtained by Carl Mitchell and his group at JPL, we also found that the liquid of hydrocarbons are mostly methane, pure methane, at least over the 50%, with a few other components such as ethane or nitrogen. Next slide, please. So our next goal now is to obtain the bathymetry of the largest sea of Titan, Kraken Mare. This will be possible only on August 2014, when Cassini will have the possibility to look at nadir, this beautiful sea. So I'm going to cross my finger because this observation is really important for Cassini and Titan. Now the microphone to Jeff. Thank you.
Thank you, Marco. Thank you, Randy and Steve. So I'm going to be talking about Titan's giant polar liquefied natural gas lakes and giant polar cap, the familiar and the exotic. Next. So we just heard about the unprecedented completeness of radar imaging of lakes and seas and the reliable depths for one of the bigger seas, and that the lakes are liquid methane solutions, mainly methane. These results are interesting from a number of perspectives. One is that they make worse a long-standing deficiency of ethane, ethylene, propylene, acetylene, and other heavy hydrocarbons. We know that these hydrocarbons are being produced by the sunlight action on the atmosphere of Titan. So it begs the question where these hydrocarbons are hiding. Now, we heard a lot about the liquids. It's also important to consider the solid environment in which the lakes exist. Next. So I'm going to give a complementary compositional perspective drawn largely from Cassini's visual and imaging mapping spectrometer, the VIMS instrument, and the imaging science subsystem, the ISS instrument. Now, I'm not a Cassini team member, mission team, or instrument team member. I'm giving a completely outside perspective, and I'm drawing from publicly released data from these teams. I want to give a special thank you to Jason Barnes and to Zibby Turtle from those respective instrument teams. So the VIMS, ISS, and radar together reveal unique North Polar materials constituting a northern polar cap larger than Greenland, as I will show. And when I use the term polar cap, I don't want to give a misimpression that this is a water ice polar cap. We think it's hydrocarbon polar cap. Titan's polar regions have a unique climate and distinctive deposits and distinctive geologic and surface processes, as Randy alluded to. So what is the composition of the polar solids? What's going on? Next. So here we have a global VIMS mosaic showing the location of the North Pole and Ligeia Mare. Next. And here's an enlarged view. You can see the dark materials. Those correspond to the lakes that the radar instrument was showing. Next. And here is just an extremely color-stretched version to try to pull out some compositional details. You see the blue materials are the lakes. Now, this is not radar eyes. This is visible and near infrared eyes. The orange materials are solid and are thought to be hydrocarbons produced by polar processes, maybe by evaporation, maybe by condensation of atmospheric volatiles. Next. So here we see that VIMS mosaic with the outlines of an imaging science subsystem mosaic at lower left. You see the bright deposits in which the lakes, the dark materials, are located, and then around that are arranged some intermediate darkish materials, solid materials. Next. And here at lower right we see an enlargement of the ISS mosaic. Next. And again, this ISS mosaic with the North Pole and Ligeia Mare indicated, and I just want to emphasize the huge scale of these features. You see at upper left the 1,000-kilometer scale bar. Next. And here we see in pink, we see an ellipse drawn around the ISS mosaic. It's not we don't see the complete ellipse, but we see a big part of it. And nestled within this bright deposit, the ellipse is just drawn around the bright deposit, but within those, the blue footprints show the radar lake materials. And you see that the lakes pretty much fall within this bright material ellipse. Next. And here is the familiar radar mosaic, now almost complete. Next. And for comparison, here's Greenland. So you see that the lakes occupy a region larger than Greenland, actually. Next. So a North Polar Lake is mainly liquid methane. We heard about that earlier. Where are the missing large amounts of heavy hydrocarbons that we know have to be produced? Some of them should be dissolved in the liquid, but we don't see evidence for large amounts of heavy hydrocarbons. What's the composition of the polar solids? Next. So some possible answers, and all of these may be at work. Several people, researchers, have talked about underground aquifers. I don't mean of water, but of heavy hydrocarbon-rich methane. That may be a hiding place. Secondly, there could be sequestration of ethane, propane, ethylene, etc., in very heavy, large molecules, organic molecules that would be solid, slightly analogous to frozen petroleum on Earth. On Titan, these substances may form solid polar caps, solid evaporites, low-latitude hydrocarbon dune fields. And then finally, I want to point out that some of my colleagues, Sugata Tan and Giles Marion and I, have produced a chemical model of the atmosphere and surface composition. We call it cryochem. It simulates Huygens probe results very well and indicates that the equatorial liquid bodies, if there are little liquid damp soils, for example, should be ethane dominated, but polar lakes should be methane dominated, as the evidence seems to be converging towards. And next, I'm going to turn it over to Linda.
Okay, well, you've heard about some interesting new results about Titan, and these results took years to gather the data and to tease out what we're seeing on Titan. Titan is a very Earth-like world, and we're now coming into summer in the North Polar region, and this could be one of the most exciting times for Titan weather. Will we see winds that blow strongly enough to create waves on the lakes, and possibly little hurricanes? As the sun climbs higher in the sky towards solstice, will these lakes possibly evaporate? So there are a number of mysteries we can still solve as we watch the change of seasons on Titan. Now there are other mysteries for Cassini to solve as well. If we go to the next slide, we are so close to summer solstice on Saturn. It'll be summer solstice at the North Pole and winter solstice at the southern hemisphere. And much like the Earth, Saturn has weather that changes with the seasons. And so we'll be watching to see what we might see with those changes. In December 2010, we saw a giant storm that completely encircled around Saturn. In fact, if you look at this image of Saturn with Titan going across its disk, that white wavy structure just below the greenish band is all that's left of that storm from 2010. Now, these giant 30-year storms often occur near solstice, so will we see another giant storm as we get towards Saturn's northern summer solstice? We're certainly going to look for that. And one of the biggest discoveries made by Cassini were the jets of material coming out of the fractures at the south pole of Enceladus. And this material included water ice, hydrocarbons, and other compounds that could indicate you have a possible habitat underneath the south pole of Enceladus. So we have a series of flybys coming up later in the mission, and one of those flybys will fly through those jets and plumes, but at a unique time, when Enceladus is near apocenter, where the plumes are most active and the fractures are the most open. So for the first time, we'll be able to make a measurement during this particular period. We'll also get to see Enceladus's north pole as the sun goes higher. Is there evidence for possible ancient fractures? Might the North Pole in the past have been active as well? And finally, just to say a little bit about Cassini's choreography, that Cassini is in a set of very intricate, complex orbits that are shaped primarily by its flybys of Titan, and we only have 4% of our bipropellant left. So we use basically a natural source of propulsion, and that's gravity assist from flybys with Titan. So we carefully target each Titan flyby, shaping the orbits, the size, the inclination, and the orientation toward our final end-of-mission orbits, where we will have the best science possible from those orbits before Cassini plunges into the atmosphere and basically evaporates. And those final orbits, what we'll be doing is going in between Saturn's innermost ring, the D ring, and the top of Saturn's atmosphere, a 2,000 kilometer wide gap, to make fundamentally new measurements about the planet itself and the rings. So we anticipate a lot of exciting times ahead. The next slide, you can find more information about Cassini, and we certainly look forward to the next 4 years. Peter?
Jonathan Amos, BBC. Would you like to hazard a guess as to how much is in Kraken? How much of this liquefied natural gas methane is in Kraken? You've got an area. If you were to apply the similar sorts of depths that you find in Lygia, what do you come up with?
Are you asking about the volume of liquid?
Yeah, absolutely.
Yeah, the total liquid volume of all the lakes at sea correspond to about 300 times to the oil reserve on Earth. But the only Kraken mare, maybe Alex is the best person that can answer to this question. You know, Alex, what is the total liquid volume of Kraken?
Times the size of Ligeia, 4 to 5 times the size of Ligeia. So if it has a similar depth profile, you'd expect it to be about 200 times the proven oil reserves on Earth. Okay. All told, the 3 mare, the largest lakes on Earth, largest lakes on Titan, the seas, take up a little over 80 to 85% of the total surface area that we have of the liquid.
Okay, and just to be clear, these lake features, they're all north of about 55 degrees. Is that right? Yeah.
So, Rick Lovett, freelance. So instead of putting that in terms of oil reserves, could you put that in terms of like comparable liquid bodies on the surface of the Earth?
I don't have volume estimates at my fingertips, but the dimensions of Ligeia Mare and Kraken Mare are very comparable to the largest freshwater lakes on Earth, like the Great Lakes. We saw the picture of Lake Michigan. It's about as long north to south as Ligeia is across, so the area is a bit less because it's skinny. The bigger lakes or smaller seas like the Caspian are comparable to Kraken. Of course, how you answer that question also depends on whether you want to just look at the number of square meters or relate it in some way to the size of the body that you're on. You know, Titan is much smaller than the Earth, so in proportion, these seas are even bigger.
And we can get you a better comparison afterwards if you'll ask us.
Irene Klotz with Discovery News for Linda. Aside from the August 2014 campaign at Titan, can you maybe go through some of the other highlights of and getting closer inside the ring? Can you go through some of the highlights of the final years of Cassini, and the is all of that? Are you going to need to recompete for a mission extension? And is the 4% fuel reserve basically now being held for the a kind of steerable reentry into a certain location for the end of mission?
Okay, I'll deal with it. The 4% reserves, we're using that now to fly the next 4 years of the Cassini mission, and our end of mission is September 2017, so about 4 more years until the end of that mission. Some of the highlights, we're going to spend about the next year coming down in inclination. We're up about 50 degrees or so inclination, getting great views of the poles of Saturn, and also that's why we're getting these radar data as well for the poles of Titan. We'll come down into the equatorial plane for about a year because that's the best time to get flybys of the icy satellites. We have flybys, 3 flybys of Enceladus near the end of 2015. We have additional Dione flybys, Tethys flybys, these close studies. Whenever you get close to an object, that's when you tend to discover things that are new and different. And in that set of Enceladus flybys is when we have the one that actually will go through the jets and the plume of Enceladus when the fractures are the most open. Oh, yeah, your final question. Well, we're going to go through a process called a senior review where all of the missions that are an extended mission, that includes Cassini, the Mars missions, Curiosity, compete in an extended mission phase for a pot of money. Right now it doesn't look like it's quite large enough to handle all of them, so there'll be some decisions made, and Jim Green can address that more if you like, to try and decide what exactly can we do, actually starting in FY fiscal 15.
Harvey Lyford, freelance. This is just a detail. Is there any difference between a lake and a mare other than the size? Are they different in some?
Yeah, well, I suppose really there is, and that's partly what this press conference is about. We've been trying to use the term lakes versus seas, which seas in Latin is maria, and we use that nomenclature on the planets. The distinguishing characteristic when we assign those names is the size, but the result partly here today is that it appears that the larger basins, the larger holes in the ground in which the big seas sit, formed in a quite different way than the small depressions that have these lakes in them.
Just to answer that volume question from earlier for everybody, Ligeia has twice, the estimate for the volume of Ligeia is twice that of Lake Michigan, and for all the lakes together is 15 times the volume of Lake Michigan.
And that was Alexander Hayes of Cornell University speaking.
Yeah, Alex is also an associate of the radar team.
Do we have a question from the chat?
Yeah, this is a question from the chat. Emily Lakdawala from the Planetary Society. Can you elaborate a bit on how the radar data tells us that the lakes are pure methane?
Marco, do that. Do you want to do that? How do we know it's pure methane?
Yeah.
It isn't quite pure.
Yeah, it isn't quite pure, but we know from lost tangent measurements, from the measurements of radar power, we deduce that the composition is probably pure methane, at least over the 50%. From the power measurements and from recent laboratory results obtained at JPL.
Probably over half of what is in the lakes is methane. There's a component of ethane and probably small amounts of others. And just in case it wasn't clear, we know that the lakes are more or less clear in the radar wavelength to radar eyes. And that means there can't be a whole lot of things in there that absorb very much.
If I can add
Sure.
just a little bit to that, just from the pure thermodynamic equilibrium viewpoint, we have some information on the composition of the atmosphere, and we have a lot of information on the surface temperature and surface pressure. And you combine all that together in a thermodynamic model, and different people have different models and the numbers come out a little differently, but basically the lakes cannot be pure methane. They have to include other chemical components such as ethane, as Steve mentioned, and probably little bits of other materials. But I think what the radar data are showing is if I understand the radar data correctly, is that something verging toward a more methane-rich, heavily methane-dominated composition is indicated. And incidentally, as my model indicated and I mentioned, the thermodynamics suggest that the polar lakes ought to be methane-dominated heavily. So, but there's other stuff in it. It's not pure methane.
Do we have any other questions? Is there anyone on the phone? And do they have a question? Any other questions from the chat? Okay, thank you very much. Oh, you have one more.
I'd just be interested in hearing Jim Green's response to the recompete.
Okay. Every couple of years, when our missions have met their primary objectives, we then have a competition. And in that competition, since we have limited resources, we're really looking for the best science that can be done. And that's called extended mission opportunities. Our next extended mission opportunities call for proposals from these missions will be issued in the next couple months, and we'll receive proposals, we'll evaluate them, and then we'll have to make decisions based on the community's review of these proposals. There are limited funds. You know, we anticipate that we'll still have a great set of missions as we move forward, but the competition is always tight. Cassini has always done well. This time we'll have Curiosity, which will have completed its primary mission as also part of the competition. But that's how it's done in our field.
Thank you. Any other questions? Okay. Thank you very much for your presentations, and thanks everybody for participating in our press conferences. This is the final press conference of the meeting, so see you next year.